Thank you. First, thanks to the organizer to giving me this opportunity to talk about my work, which is in collaboration with Sarah Collins, Padmanath, and Sasa Pilosek. So the title of my talk is Exotic Tetraquark in CC Q-bar channels. Here Q-bar is any light quark. So to start with a basic introduction, we have the theory of strong interaction, which is QCD, and this is the Lagrangian QCD. And unlike QED, the force mediator here is gluon, and a special property of this is that here we can have self-interacting gluons, and as a result, at very low energies, the QCD becomes non-perturbative, and the QCD. This is the plot of QCD coupling as a function of scale. So as you can see that at low energies, the coupling is very strong, and this is also called as hadronic regime or non-perturbative physics. And at large energies, it is perturbative regime, and this is also called as asymptotic freedom. So the regime that we are interested in is the hadronic regime, and for that we have to use some non-perturbative approaches. And one of the non-perturbative approaches or first principle investigation is lattice QCD. So just a small introduction for hadrons. So the textbook definition is that hadrons are composite subatomic particles made of quarks held together by the strong interaction. And we have some standard hadrons like baryons and mesons. So as an example for baryon is proton, and mesons we have pions and kaons. But recently we have also found some exotic hadrons, which are like tetraquarks, which are like composite objects of 4 quarks. And there are other structures also, example pentaquarks. And in all our calculation, we assume isospin symmetry and only strong interaction is there. So so this is the summary of hadrons that were discovered in LHC last 12 years. So on the x-axis, you can see the year of discovery, and this is the center of mass energies and GeVs. So you can see that there are various hadrons that have been discovered. There are like 75 new hadrons that have been discovered. And there is summary of exotic discovered in last 12 years. So you can see that there are like pentaquarks and some tetraquarks, and also this pentaquark that was also discussed by in the morning talk by Jim. So so of all this exotic hadrons, one of the most recent and interesting one is this TCC 3875, and this is interesting because this is the longest lived exotic till now. And let's see what are some of the special properties of this TCC. So this was discovered by LHCb as an exotic narrow resonance, and its mass is like 3875 MeV. With an electric charge of +1, and this is an isoscalar state with quantum number 1+, and as I just mentioned that it is the longest lived exotic discovered till date. Now, if this was the signal that was found in the experiments, and one can see that this was found in the mass distribution of d0 pi plus, and this was found very near to the d star d threshold. So this green line is the d star d threshold. So there were many d scattering studies, including lattice calculations, to explain this state. And one of the first one where they extracted the scattering amplitude from lattice and also find the pole position was in this reference. And the next potential candidate and thing that I am interested about is the next potential candidate that could be within the reach of LHCb would be a tetraquark with flavor content CCU bar S bar. So the flavor content of TCC was CCU bar D bar, and if we just replace the D bar with an S bar, so that's what our motivation is. So now, as I just mentioned that we need non-perturbative approaches. To start with just a small brief introduction of lattice QCD. So lattice QCD is a non-perturbative gauge invariant regulator for the QCD path integral, and in this we redefine the theory on discretized Euclidean space-time. And the phase space of QCD is sampled using important sampling procedures such as Markov-Chain Monte Carlo algorithms. Now, an important quantity that one use to measure all these energies is correlation function. So what one does is to devise some operators or interpolators with desired quantum numbers that one want to study, and then they construct these correlators. So if one does the spectral decomposition of these correlators, we can get this form. So you will see that the correlation gets contribution from various different states of that particular operator. So you can see that there are various excited state contribution also. And if one wants to extract the ground state corresponding to that particular operator that we have used, one can take the last time limit. As you can see, at last times the correlation function varies like this. So here is a plot to show this thing. So in log scale, the correlation function as a function of time varies linearly, and if we plot the slope of this plot, we get a behavior like this. So this is like a falling behavior, and at last times it plateaus. So one can extract the ground state if we fit this region and extract the ground state energies. So that is just for the ground state. But what if we want to go beyond the ground state? So for that, what one can do is to construct to use a basis of operators, not just one operator, but use multiple operators, and to create a correlation matrix out of it. And then one can variationally determine the optimal linear combination of these operators to describe the time evolution of the excited states. And this is also called as variation procedure. And in this one, basically, it solves a generalized eigenvalue problem. Yeah, and once we get all the finite volume energy states, we can construct what is called as finite volume spectrum. So we'll spend some time on this. So this is finite volume spectrum for the TCC, which was taken from the reference that I mentioned earlier. And so here on the x-axis, I have lattice volume, the volume of my box. On the y-axis, I have center of mass energies in the units of dd star threshold. This black curves are the non-interacting levels, which means if my two particles are not interacting, then what would be their energies? While this circular markers, are the energies that we extract from the lattice calculations. So the physics that one is interested in here is that to see the shift of this lattice energies with respect to the non-interacting levels. So if the markers are negatively shifted with respect to the non-interacting levels, then the interaction is attractive. But if it is positively shifted, then the interaction is repulsive. So from this, we can at least expect that whether a bound state could exist or not. And so this is spectrum at 280 MeV by ion mass. And a thing to note here is that these are finite volume energy levels, and associating them with infinite volume physics is not so straightforward. So once we extract the finite volume spectra, how to extract the infinite volume physics? That's the main question. So in infinite volume scattering, we have continuum of states. If we have two particles of mass m, so we have this continuum of states, scattering states that we will have in experiments, and from that we can, in an experiment we can have like extract the cross section, and from that we can also extract the partial wave. Sorry, phase shift. But on lattice we don't have access to the continuum of states, but what we have are finite volume states, and it's not so trivial to map this thing. And Meine and Testa in 1990 gave a theorem that it is not possible to extract the infinite volume physics from just a single finite volume energy spectra. So what's the way around? So Lucier in 1991 devised a relation, which is this relation. I will explain it. And using this relation, one can in some way extract the infinite volume physics from the finite volume spectrum. So what this relation is, so here they are taking a determinant over infinite volume scattering amplitude. So this is infinite volume scattering amplitude, and this is matrix of non-mathematical functions. So Lucier kind of gave a relation which connects the infinite volume physics with the finite volume physics. So if given a finite volume spectrum, you can kind of constrain the infinite volume amplitude. So here k tilde is the infinite volume scattering amplitude, and this is related, this might look too much technical, but it's not that technical. So the scattering amplitude is related to the transfer matrix in this way. And yeah. So if you use Looser's relation, then what one can do is to we can use this finite volume spectrum to constrain the amplitude more. But just a single finite volume is not enough to constrain the amplitude in many cases. So what one does is to use various different momentum, left frame momenta, like your box frame momenta. Your box is moving. So we can have like box at rest, box at 1. So these are units of 2 pi by L, since when we are in finite volume, the momenta is quantized. So this is in units of 2 pi by L square. And if we include more and more momenta, we can constrain the cross section and amplitude more and more. And what we can do is not just consider a single volume, but we can consider multiple volumes, and then we can try to constrain the amplitude more. And yeah, so once the infinite volume scattering matrix is extracted, we can extract various physical quantities from that amplitude. And employing these techniques, the first lattice calculation for TCC was performed at 280 MeV by mass, and this was the reference. And the authors in this paper identified the pole singularity in the amplitude, which was found to be linked to the physical state that was found in the experiment. And they examined various Riemann sheets, which is associated with the unitary cut in the amplitude. But that I will show you in the next slide. But the main question is, can we predict existence of any such solutions like TCC-US in the CC U bar S bar quark configuration? And that's what my motivation is. So this is the contour plot of cross section. So these are the two plots for physical sheet. This is the contour plot, and this is the CD plot, and this is for the unphysical sheet. So you can see that this is the pole that they find, and yeah. So this is the result from the PR paper. Yeah. Now that was for the TCC case. Now we comes to the D star DS star spectrum. So this was the spectrum that we found in our case. Now, just from the spectrum, you can see that it is a rich spectrum, and it is a relatively difficult system because it has multiple final two-state meson configurations, and there are also some potential mixture of attractive and repulsive interaction in here. And this is also complicated because this is a coupled channel scattering. So we can look at the spectrum. So here we have again finite volumes. The volume of my box. This A1 plus A1 minus are the finite volume irreducible representation, and on the y-axis I have center of mass energy in units of ds star threshold. So here the interesting parallel to see is this one, this T1 plus. So these are like this irreps are like box quantum numbers or quantum numbers when you have finite volume. So the TCC was found in 1 plus quantum number, and that 1 plus quantum number can be the 1 plus quantum number can be seen in this T1 plus irrep. So if we look at this particular region, so the below one is the DDS star threshold, and the above one is D star DS threshold. And one can see that the DDS star energy levels, the lattice energy levels, are shifted downwards, while the above one are shifted upwards. So this is showing kind of like a repulsive thing, and this is showing attractive behavior. And our further analysis showed that this kind of behavior is being shown because of the coupling between the two channels. If there were no couplings, then this energy levels would be almost on top of the non-interacting levels, which would show that there is no interaction. So so I would say that this is still an ongoing analysis, and the analytic structure of the scattering amplitude across the complex plane is still being investigated. So I won't say to take my results as final right now, but so I will still show you the contour that I have found. So these are various. So since I am talking about a coupled channel scattering and there are multiple channels, there are multiple Riemann sheets as well. Like and this Riemann sheet different correspond to different sign of the DDS star momenta. So in the first sheet you can see that no such. Here in this plot we don't see any interesting poles. We did find some interesting poles, but those are not in the immediately physically interesting regimes. So so this is the summary of my talk. So there is a lot of experimental activity going on in this field, and exciting new hadrons discoveries keeps us motivated and active, as Jim was also mentioned in his morning talk. And lattice QCD is one of the powerful non-perturbative first principle approach for studying hadrons. As Professor Murthy just mentioned yesterday, that lambda 1405, which was found as a molecule, has molecular nature, which was proposed by Professor Rajashekharan decades ago. And various details on extracting finite volume spectrum were discussed. And I also mentioned the Lucius prescription for infinite volume scattering amplitudes to determine from finite volume spectrum. And I also discussed the results for TCC and ongoing D star scattering studies. So, thank you.
Questions? So to extract this poles, how large volumes you have to take, or how final lattices? So how sensitive it is to the choice of your volumes?
So actually, this poles that we have extracted are for infinite volume amplitudes itself. So we use the Lucius prescription to extract the infinite volume amplitude, and then we look for pole in the infinite volume amplitudes. Not in finite volume.
Yeah, but the finite volume spectrum also you have to do it very fine so that you can resolve all the things on the phase shift curve. You can resolve it very well. So how large volumes you have to take?
So yeah, I mean, of course, if we have large volumes, then
so you have to do a more momentum resolution, I guess.
Yeah, we have to use various different. I mean, it's not just a large volume, but we have to take multiple volumes actually, so that we get more levels and more we can constrain, because Lucius relation relate any finite volume to any infinite volume thing.
But can you use arbitrarily small volume to give this?
Then actually there would be some finite volume effects. It depends on what hadron you are studying actually, because then if it is a very large hadron, and then if you're taking very small volumes, then there would be some very large finite volume spectrum, because actually Lucius said that the finite volume effects are exponentially decay. So if you are taking very large volumes, then the finite volume effects would be very small for that particular case. So yeah, of course, large volume does help. Yeah.
So just a very basic question. So is CC bar and 2 light quarks, is that also possible? Or?
Yeah, yes. So there are actually, I guess. I guess here. So this is like exotic, and you can see, I guess, we have some CC bar kind of thing.
So 2 light quarks?
Yeah, CC bar and QQ bar.
Yeah. And would they be similar properties or very different, or what?
Similar in what sense? I mean,
in terms of the masses.
So yeah, not sure in terms of masses, but you can see that this pink one are the CC by QQ bar thing, and they are like, yeah.
So where is the state that you discussed in there? See? Oh, your state is not in here.
This one is this.
Yeah,
so
okay.
So TCC is here, and TCCU is still not found actually.
Okay.
So